other materials, this is a unique a material property, and for soil, for rock, and for other materials, this is there's a certain ratio associated with for those just joining, please register your attendance. There are certain ratio associated with each material, and it's a unique material property, so to speak. But because soil is non-homogeneous, it's a little is not as straightforward as for the case of water. So in most engineering materials, specific values of the ratio of horizontal stress to the value of vertical stress exists. That ratio is called the lateral. That's in fact the what we call the lateral earth pressure. That's what is called the lateral earth pressure, that ratio. So if you can see on your screen, the ratio of the vertical stress to the horizontal stress, that's what you call the lateral earth pressure. However, the soil is balanced. There is no excavation, or if there is, the excavation does not influence the stress ratios. So also note here that the total stress now would be the effective stress, whether it's the horizontal or the vertical, plus the pore water. So again, sigma V would be sigma H plus the pore water pressure. Of course, the pore water pressure is simply the gamma water times Z of water. So if water were on the surface here, if water surface were on the surface, then this same height would be Z water. So that should be very simple. And of course, the sigma V, it would be just gamma sat. You should already know this, gamma sat times the Z. So when you have two of these, you can know what the excess pore, the total and effective stress parameters are. Okay. So use the pore water pressure, which is the summation of hydrostatic water pressure and excess pore water pressure, or simply put, use just the pore water pressure. So for cohesive, it's very simple here. Okay, I also need to question you here. This U is just gamma water times Z water, if at all there is no external influence, because of course when there is excavation, and the interaction there will affect, of course, the pore water pressure, so it will no longer be simply this value, right? But for the natural condition where there is no excavation, there is nothing else, then so if the water is on the surface there, then the pore water, of course, would simply be gamma water times Z water. Now, in cases where the excavation and all this, the excavation is affecting the stress rate, then we have sensors or transducers that can be put inside the soil to help us to tell us to measure, in fact, with precision, and tell us exactly how much the excess pore water pressure is. Now, the value of K naught, we already talked about this, so it should not be a big issue. From jacking is 1 minus n phi prime. in the previous topic, there is of course it's more the formula is this is a simplification. There is some value of there is some the equation itself is more complicated than this, but in fact this is a simplification which can give you more or less. The simplification can still give you reasonable data, but I just need you to see the full equation. The equation in full the equation is this is the full equation here. There is some ratio here, but we just taken this part. So here anyway, you've seen the equation, so this is a simplification. The simplification still can give us reasonable results. So phi is the effective normal internal friction angle during friction angle. Now this is I've said this is an effective stress parameter. So if you are doing the experiment, you have to work with effective stress, not total stress. So if this is sigma, and this is tau, and then you draw your line equation. This is phi prime. So this is the value here. Should be very clear. Now, but this is for what is called normally consolidated soil. Now, normally consolidated soil. Okay, I have to try to explain. Now, this we already talked about the the 1D consolidation test. 1D consolidation test. Consolidation test. Consolidation test, and if you draw so this is the E, you usually get a nice curve like this. Now if you draw some tangents, the tangent to those two parts, then you read down here, this is what is called the pre-consolidation stress. So we usually call it sigma P or sigma V, V naught. Now this is what I was saying, that clay will remember the highest load it has ever carried in its lifetime. So if the highest load it has ever carried in its lifetime, sigma P, let's say for argument's sake that this is say 100 kilonewtons, then for some reason after some time it carries a load of sigma, say 50, because it's carrying less load than it has ever carried before. That is over consolidated. Is called and the over consolidation ratio, OCR, is the pre-consolidation stress, sigma P prime, over the current load. current load. So for this one, the overconsolidation ratio of current load. Anyone for this one, the overconsolidation ratio would be how much? Just make sure we are communicating. For this particular example, what would be the overconsolidation ratio? Classwork? Hello?
Hello.
In this case, what would be the overconsolidation ratio? Yes?
0.5.
Really? Sigma P over the current, which is 100 over 50, is 0.5. Really? That's 2 years. So the highest load over the pre-consolidation ratio is there. It will always remember that highest load. So this kind of clay is what we call over-consolidated clay. So for over-consolidated clay, the OCR value, the over-consolidation ratio, is always greater than 1. So if you see the OCR is greater than 1, that is over-consolidated soil. In the same breath, of course we don't use this for normally consolidated soil, but for argument's sake, for normally consolidated soil, it means the load it will be carrying would be more than 100, so 150. So for normally consolidated clay, for argument's sake, for NC clay, for argument's sake, the OCR value is less than 1, because if you take the current load would be higher, the pre-consolidation ratio would be 100 and the current load would be 150, so the OCR value is 1. So please note that difference. Now this is what I was telling you yesterday about triaxial test. So once you do with triaxial test, you need to do with clay, you need to do this 1D consolidation test, find out what this value is. The value you use for consolidation, which is a uniform pressure. You remember consolidation is we apply a uniform pressure in the sample at the consolidation stage. So this is the value you use at consolidation stage. This value should at least be equal to the sigma p from the 1D consolidation test. That value should be, and it's one uniform pressure. And what is done in the process of consolidation, if the value you're going to use for consolidation is 150 kPa, the pressure applied one at a time. So the machine will apply one uniform pressure, 2, 3, 4 until it reaches 150. So when it reaches 150, and this assuming 150 is greater than sigma p, then beyond that it becomes what is called normally consolidated soil. That's what we want for this experiment. That means the stress history effects have been erased by the loading. And just a little bit, because I'm not sure if you study this ever again, this of course there's some theory on this part that we are not going to get into, but the idea here is that this is called the virgin consolidation line. This part of this curve. So you need the sample under test to be on this virgin consolidation line. So you can see now this value is the value at the start of this line. So this is y. So sigma p. So if you consolidate with any value here, you can see that this value is less than sigma p, and this the state of the sample will not be in this line. So that's why the value you use for consolidation must at least be equal to, or at least slightly higher than sigma p. So for reference purposes, the value for consolidation is always you can say is equal to the pre-consolidation stress. You can add a few kilonewtons, 1 or 2 higher than the pre-consolidation stress. Okay, so please note that this is why I was explaining the issue of normally consolidated and over consolidated. So this is for the over consolidated clay. This is for normally consolidated clay. We use this equation. Now for over consolidated, because this is you have seen that the soils are not the nature or the stress history is not the same. So then for over consolidated clay, this is the K from the normally consolidated soil, which is estimated from here, of course with the over OCR ratio, which I've shown you how to calculate. So this is the coefficient of lateral earth pressure at rest for over consolidated soil. OCR, of course, is the over consolidation ratio, and K naught is the coefficient of lateral earth pressure for normally consolidated soil, which is estimated by the Jackie's equation, and alpha, this value here, is estimated as sin phi prime. Now these values for normally consolidated soil is reasonable and reliable, I should say. Now for over consolidated soil, this equation, so equation 3 is reliable for normally consolidated soil. Equation 4 is not very reliable. One reason is that because of the consolidation process is quite complicated. Okay, we'll explain this later. But the idea is that this for equation 3 for normally consolidated soil is reliable, but equation 4 is not very reliable for normally consolidated soil. Now one reason is because the process of consolidation is complex, is not very simple. But before we get there, this is what I was telling you, that the over-consolidation ratio is the pre-consolidation stress divided by the current vertical stress. And for normally consolidated ratio, clay, the OCR value is less than 1. For over-consolidation ratio, the value is greater than 1. Typically, we don't use OCR value when it comes to normally consolidated clay, but for argument's sake, so that you can see the difference, the OCR value for over consolidated clay is 1. Now these are part of the test I showed you, whose stress path I showed you yesterday. Ignore everything else. All I want you to see, this is for my thesis, for my master MSc thesis. These are the tests. Ignore all this column, all these other columns except the effective stress column and the OCR, because this is what I want to demonstrate. Now for this sample, the pre-consolidation stress was 76.7. So 76.7, that's the pre-consolidation stress. The current stress they are carrying, in the current vertical stress was, you can see, is less than 76. So over consolidated soil. So if you divide the current value here is the pre-consolidation stress is 76, and then the current is about 46. So 76.7 divided by 46 get about 1.7. Okay, I know OCR of 1.66. when it's 45, an OCR of 1.69, and here an OCR of 1.6. Now, so this sample here for CIUA, you can see is normally consolidated because it's carrying more stress than the pre-consolidation. I think this is important, you need to note. So I've said, if you can see now here, the vertical stress is higher than the pre-consolidation stress. So for argument's sake, just to make sure you people understand. So for this one, the pre-consolidation ratio is 76.7 divided by 46.26. Okay. So for this particular one, if for argument we usually don't do this, the pre-consolidation ratio will be 76.7 divided by 96.5. You can see this value should be less than 1 and this is more than 1. So that should really give you a clear idea of the what the pre-consolidation ratio is. Okay, if you need more of this, I can show you in the thesis itself. So for the so for the what I was telling you, this I think this is a very I'm going to tell you in a very simple way. For this, so this is what you're talking about. So this is the virgin consolidation line. This is the virgin consolidation line. This is actually, in fact, this is an actual test. Okay, let me snip it so it is easier to explain. Okay, let's so this is what I was saying. If you draw the void ratio and the load, and of course this is the nature of the curve. Now this is the virgin consolidation line I was telling you about. Now usually the easiest thing to do to get this point is to draw a line. You can see the black one and the line here to get the pre-consolidation stress. So the easiest way is to do this, is to draw a line like, you can see those two lines meet here. That's the first thing to do. However, this is a debate actually. There's no agreement on what exactly to do. Of course, the estimations from either of the methods should be the same. So you draw a tangent, and the tangent there where they meet is the pre-consolidation stress. Another guy, some other authors, the method I've used now, suggests you can take the point here, draw two lines, the angle, the maximum angle at the point that this curve increases, the gradient changes the maximum. That point you draw these two lines and then bisect, get the this. So you draw this and draw that, find the midpoint, and when it meets this part, that is the pre-consolidation stress. So you either, the simplest one is just draw the tangent to the circles where they meet, the curves, the two parts of the curves where they meet, that is your the pre-consolidation stress. So this is what I was saying. So this is how we got the 76. You can see this is 100, so this is 90, this is 80. So the value there is around 76 as we have used there. And this is the idea of the virgin consolidation line, such that if the value of pre-consolidation is higher than this, then the sample is in this line. Okay, so that's with the issues of consolidation, and then we've said question 3 is satisfactory for consolidated, normally consolidated clay, whether they are cohesive or cohesionless. For over-consolidated soil, nevertheless cohesive and cohesionless alike, the results of question 4 are not reliable, relatively unreliable. One of the reasons that the formation process of over-consolidated soil is complicated. So this is a point. So this equation for non-consolidated soils, both cohesive and non-cohesive, are reliable, but this equation is not reliable. The reason preferred is that the process is complicated. So this is the basis of the theories of earth pressures. Now the best way to deal with the issue of a consolidated soil is just to do in situ test, where you find the ratio. You can actually measure, there are ways that you can measure the vertical and horizontal stresses. So to find exactly the ratio, the K, the best way is to do in situ a test to monitor the ratio of the stresses. Okay, so now to estimate these stresses, so let me go back here. So here we assume that for the at rest pressure, this excavation had no influence on the, so a situation like this, the excavation here had no influence on the stress state. Now if now that assumption is not there, and of course in reality when you sink, when you do an excavation in this nature, the reality is this part will be affected by the equilibrium of the entire excavation. So if that is the case, this part, the reality is that this retaining wall is gonna deflect like this, will deflect like that. That means the soil will tend to move, to push the wall that way. So that will interfere with this ratio, and therefore on this side on this side, I think we had already talked about this. On this side, this would be sigma V, but this now would be active Ka sigma V. So for this part, and here this would be sigma V again. So sigma V on the active side, let me call it active. This would be sigma V on the passive side, and the value here would be Kp, and sigma V on the passive side. So the point is, when the excavation has influence on the equilibrium, then this is called the active side. Active side, and this is passive side. So these values are, you've seen that the way we calculate the K naught for at rest when the excavation has no influence on the stress state. But now when there is imbalance, one is active side, another one is passive side. The reason is that here on the active side, the soil is tending to move away. The soil is tending to move away, push the retaining wall away. On the passive side, the soil is tending to push the this one is pulling against the soil. Let's say, okay, let's talk about the movement of the soil. The soil is moving the kind of, there is some extension. Okay, let's the soil kind of is undergoing some form of extension, but here the soil is going, the way to look at it, maybe the soil is undergoing some form of compression by pushing the against the retaining wall in this manner. So this passive and active side. So then the ratio, this K naught is no longer equal to 1 minus sine phi, like we've talked about. So this K naught becomes either Ka on the active side or Kp on the passive side. And so now these theories are helping us to estimate Ka and Kp, because you can see it's not a very, because of the non-homogeneity of the soil, then it's not a very simple, straightforward matter like the case of the lateral earth pressure at rest. So for this reason, we have different theories to estimate these values Ka and Kp. We start with the simplest, the Rankine. Now Rankine made some assumptions. Let's get to the assumptions first. Rankine, so these are the assumptions that the Rankine made. The soil is homogeneous isotropic and possesses an internal friction and is in state of plastic equilibrium. So that's the first assumption. Number two, the failure surface is plane surface, is level or uniformly sloped. Number three, that the shear strength is mobilized uniformly on all potential failure plane through the backfill. That the presence of wall does not influence the state of stress in the backfill. The failure is two-dimensional problem. So in a nutshell, the assumptions of Rankine is like this. So that if this is your excavation, first he says that of course we know that it's always, the failure there is always a slip circle, but for ranking he assumes this. Okay, this is only true to limited extent when the for very so this one depends on the slope as well. So if you have a very shallow slope, then this failure might happen. But if you have a steep slope, we know for sure that is always a slip, kind of a slip circle surface. But these are his assumptions. At some point it converges with the other theories, but under certain simplifying assumptions, which we are going to talk about. So and also he assumed if this is the wall, there is no friction between the soil, there is no effective friction between the soil and the, so if this is the soil and this is the retaining wall, this is the retaining wall, there is no friction between the soil and the retaining wall. These are his assumption, and also this is a two-dimensional problem. Of course, these assumptions of also the shear strength is mobilized uniformly here. We've said that tau equals C plus sigma tan phi. You should already now be very familiar with this tan phi. So this is mobilized uniformly along the failure plane. So those are the assumptions. So let's get now to the, unless there's a question, let's get now to the details. Excuse me. So the theory, Rankin developed theory of lateral earth pressure in conditions of failure in front of and in the back of retaining wall on the basis of the concept of plastic equilibrium. We are saying in front and in the back because failure we can either have passive failure or active failure. So here, this is what we are saying. We can have passive. So on this side, this is passive failure or active failure on this side. Okay, so this side, this is active, and this side, this is passive failure. So that's why we say at the back, I don't know which one is back. If you say this is the back, then this becomes the front. If this is the front, this becomes the back. So that's what we are saying. So we have two. All we are interested in to get Ka, which is for the passive active side, and Kp for the passive side. So that's the point. So figure 3a shows the parameters of Mohr-Coulomb failure line, both in front and on the back of the retaining wall, are C, and I think this is something is wrong. So C and phi, I believe, so should be can rectify that. So the C and phi So suppose there exists no friction between the retaining wall and the soil, so the same assumptions, and the earth pressure both in front and back of the retaining wall is K naught before the retaining wall moves. The vertical stress sigma V, the vertical stress, let's see, sigma V at X and Y. So the sigma V at X and Y near the wall at the, so before the let's see, the diagram. So before any so here yes, so the idea here is, for example, the before you do anything, so assume you have put the retaining wall there and you did not excavate. So somewhere here, somewhere here, whether on the passive or the active side, this sigma V should be the same, right? Sigma V and sigma V in both sides should be the same. That's the point. So if you draw, and the stress conditions can be represented by the Mohr circle C. So the Mohr circle in figure 3b, so here. So then so and then in figure 3b, so due to the earth pressure on the back of the retaining wall, the wall is pushed toward AB. So this is what I was trying to say. So because of this, the earth pressure the wall is pushed. I think it's shown, as already shown, and the horizontal stress decreases while the vertical stress condition is unchanged. I think intuitively you should see this, because the wall is moving this way, the horizontal stress will reduce a little bit. All right. So if the horizontal stress will reduce a little, but the vertical stress remains the same. So then, that's the point. That's what what the explanation is. So the Mohr circle grows larger and will intersect at a point with the Mohr Coulomb failure line when the soil at X is at failure. So the type of failure is called active failure, and the lateral pressure on the retaining wall is active pressure as represented in circle A. So this is circle B and circle A. So the issue here is that here there is a ratio, there is vertical stress and the horizontal stress. Now because of the space here, the soil has to move to a point of balance. So because of this, the sigma h will reduce, and the representative more circles are as shown. So initially this is the more circle, right? Initially when there is the state of balance sigma h and sigma v, when the soil moves, that means sigma h reduces, then the circle becomes bigger to touch the failure line. By intuition, of course, on this side the pressure is going to increase, so the ratio of sigma h, so if this was the same circle, so sigma v and sigma h, on this side the sigma h reduces to touch the circle. Now intuitively here you will see that sigma of course here sigma h will flip, will become to sigma 1, because sigma h now will become bigger, but because of the squeezing, this value is quite high, will become very high, and I told you always Kp is always greater, maybe greater than 1. So then the sigma 1 in fact will increase. Because of the increase, the more circle will expand to touch the failure line here at the bottom as well. I believe that is the same explanation preferred. So two things. This is important. So at the balance conditions, when so here, okay, let me try to make it. So here, when you have done no excavation there, so the ratios of sigma v on each side to sigma h is the same. To sigma h is the same. Okay, it's to sigma h is the same. So then that is represented by this small circle. Okay. Now when you have done the excavation, so I have to redraw. When you have done the excavation, so this the soil tries to squeeze away or push away the retaining wall. So this value will have the same sigma 1 v, but this value is reduced. We have a different value of sigma h in the active, which is reduced. So when this value is reduced, so this was the value of sigma h initially. When it is reduced, the value will move to this part. That's the point. So you can see sigma v is the same, but the sigma h is reducing. So that means the diameter of the circle is increasing, and then we have a different circle. And that circle has the potential of touching the failure line. Remember, this is phi. From the theory we've already established, and of course here we are assuming the soil has some cohesion, so that's why it's closing this tau at some value. Now on the intuitively on this side as well, on this side, if this increases, so here you need also to note, normally this is called the highest value is sigma 1, so this will remain the same, sigma v remains the same, but because of the squeezing, you can see this is pushing, the soil is pushed this way. Of course here the retaining wall has also moved this way, so the soil here will be under squeezing, under compression, and so the sigma p in the horizontal direction will be very high. Okay, now here sigma, the same idea, so sigma 1, sigma h, but the because normally the highest value, so of course here if sigma p, actually here kp, the kp sigma p over sigma v is actually greater than 1, so it means that the sigma p now is the one like sigma 1, is the one like sigma 1, so expands to this point. Again the radius of the same circle has increased, and then you can do as you can see the circle is expanding to touch the failure line as shown. So that's the basis of the formulas we are going to derive. So here basically from geometry as well, so sin phi, so if this is the phi is this angle, phi is that angle, so from geometry, and this is 90 degrees, so this sine inverse of phi is sine is this this side over that side, which this is what we are shown. So AB over AO, which I believe here AB, where is AB? No, they're using this one. Okay, they're using the small circle, so AB over AO, you can see that's okay. So if this is 90, then sine is AB here over AO, okay, what we're trying to do here. We can resolve, you can now represent them in you can replace this. For example, you can see O prime is just O prime plus OA, so that's just issue of trigonometry the geometry, and then AB is just the sigma. You remember we said sigma 1 minus sigma 3 over 2 is the same thing. So this is just the radius, this is just the radius, and this you can see based on the just a minute. Of course, from OA is the sigma 1 plus sigma 3 over 2, isn't it, from this, but the this part can be calculated based on, because if you see tan phi prime, phi would be this side, so this side, let's, I don't know, call it x over OO, but x is C, so you can find the value of OO, which is cot. this is what they're saying here, C cot phi, of course, plus the center. This is, I think the rest of this is just geometry. So this is the root of that equation anyway, the root of the equation, and so which you can simplify. If you want now to get sigma A, this is just econometry and geometry, you can solve for yourself. So this is how to get sigma A, and sigma Ka, of course, is sigma V tan squared phi over 45 degrees minus phi over 2 minus 2c tan phi. So this basically means that on the when C is 0, you remember the source we were saying sigma this. So when C, if C is 0 source, this part is 0. This part will, for source that are 0. In any case, okay, now so here we are saying sigma A so sigma A, which is sigma H actually, A is sigma V times Ka minus, of course, so this is why we are saying that K of course is sigma H over sigma V. Of course, for when we assume there's no cohesion, when there's some cohesion you can see. So this is why we are saying here now that sigma H is Ka sigma V, but of course with cohesion you have to subtract this part, root the Ka. So now this is your formula, but the point now, this is the how to get the coefficient of active earth pressure. So this is Ka from Rankine, and I think I already mentioned this before. Ka is tan squared 45 minus 5 prime over 2. I think this one we already talked about in detail. So now here this part was already introduced, but now we talk about this in detail. So this is the basis of all this derivation, and this is, so you can see this angle showing up on the active side. The failure is the theta is 45 plus phi over 2, and the passive side is 45 minus phi over 2. Those angles are important. So then Ka is the coefficient of Rankine active pressure, which is tan squared 45 minus phi over 2. According to the Mokulon failure theory, there forms a failure zone behind the retaining wall, which is the active zone, where the soil is all at failure. The failure surfaces forms angles of 45 plus phi over 2 with the horizontal. See figure 3c. This figure. From figure 3b, the earth pressure distribution behind the retaining wall can be obtained at a theoretical level, as shown in 3a. Figure 3a shows the earth pressure behind the wall pushes the wall forward in front of the wall at depth z below the ground surface. The lateral stress at y increases, the vertical stress stays constant, thus the corresponding circle grows smaller. When the lateral stress exceeds sigma v, However, the Morse circle will begin to grow larger when the Morse circle intersects the point with Mokulum failure, so that Y will fail. The above failure type is called passive failure. So this is the part I already explained, that here the sigma H is going to grow smaller. Here for a moment sigma H grows smaller, but because of the squeezing, the compression, it gets bigger until it crosses this other side, and so the Morse circle grows larger until it touches the failure envelope. So similarly, from the same, because we already derived the first one, so using the same logic, then we can derive the sigma P as shown. So please note how different sigma P and sigma A is. So Ka is 10 squared 45 and minus 5 over 2. Now Kp is this, okay? So the passive failure, and of course Kp is usually larger than Ka. So if you compare Kp is larger than K0, which is larger than Ka, which you should now be familiar with. So Kp is the coefficient of Rankine's passive earth pressure. Similarly, according to the Morse failure theory, the failure zone where the passive failure happened is called a passive failure zone. The soil in the area is all failure, whose failure surface form angles 45 minus 5 over 2 with the horizontal, as shown in 3C really, in 3B I think, or in 3C. Yeah, this is the diagram. Okay. 3C. So suppose the wall moves forward by such a great distance that the soil before the wall is completely passive failure. The distribution diagram for the passive pressure before the wall is also shown in 3A. For effective stress analysis or drained analysis, the Mokulum failure line should be expressed in terms of C and phi. So here, because of the difficulties we already talked about, the same formulas, but now in terms of effective stress, you can in terms of effective stress, you can use the effective stress parameter. That's all we are saying, but you can do a total stress and effective stress. But now, of course, we expect that the effective stress analysis should be much more reliable or more accurate. So you can express the same things for the active side. This is the active side in terms of effective stress. So where the coefficient, so here the coefficient of Rankine active and passive failure, and the angle between the active and passive, I think this is not right, should be, so this one needs to be expressed in terms of the in terms of active, I mean so for total stress and drained analysis of clay, phi equals 0 concept is applied as shown in figure 4. figure 4, assume the sigma V and the undrained shear issue of clay at the bottom x, y are the same. Note, as a matter of fact, they may not be the same x and y. So for undrained clay, I think the practice is to assume, this is what we are saying, to assume the UU. So for undrained clay and undrained or for saturated clay, this UU concept that we have talked about for undrained clay. So this is sigma, and we're talking about total stress parameters. We usually assume we usually assume so that we don't bother with phi. We say that this is SU, and we're saying the phi u here is assumed to be 0. So this is, remember, for saturated clay. So the phi equals 0 is more preferred in the solution, as you have seen or as explained. So class rep, I think we stop there. Unless there's a question, we can stop there and proceed on Friday to finish the remaining part. So just to let you know, there are two theories: the Rankine theory of how to calculate Ka and Kp, and of course there is another one called the Coulomb theory. Now Coulomb considers a little bit more. You can see that Rankine made some assumptions which are fine, but in reality they don't. It turns out they are probably an oversimplification. So now